Hi everyone, thank you all for tuning in. Today I'll be talking about our work titled Approaching the Quantum Singleton Bound using Approximate Error Correction. And this is joint work with Louis and Sam. And I should say thanks to Louis for the inspiration for many of the diagrams in these slides. Great, so to begin, I wanted to recall the basic setup of error correction. So typically in error correction, the goal is to encode some message M into some slightly larger ciphertext or code word C, such that even if we were to tamper with the delta fraction of the symbols of C, we would still be able to decode and recover the message M. Just to rewrite the goal, if we take any message M, encode, tamper, and decode, we recover M with high probability. Our work is about quantum error correction, and in quantum error correction, the goal is quite similar. Now we start with some code state psi, and psi is defined on a tensor product of small Hilbert spaces, and it might even be entangled with some other register H prime in purple. And subsequently, we encode and tamper with a delta fraction of these registers and decode, hopefully, to recovering psi. Just to formalize and quantify this goal, we take psi, encode, tamper, and decode, and the goal is to recover psi in a metric known as the diamond distance, which for all intents and purposes in this talk can kind of be understood as statistical distance or total variation distance, but with entangled inputs. Great. So if you know anything about quantum mechanics, you may have heard about the no-cloning theorem. The no-cloning theorem basically says that there's no physical procedure to take an arbitrary quantum state psi, encode it, possibly manipulate it into two other systems, and recover the original state psi from both of those systems. Perhaps unsurprisingly, this no-cloning theorem imposes a fundamental limit on quantum error correction, which manifests in terms of a bound known as the quantum singleton bound, which says that no quantum error correcting code of certain rate r, which is the ratio of encoded qubits to physical qubits, can possibly correct from a fraction of errors delta more than 1 minus r over 2. And this bound is quite robust in the sense that it makes very little reference to the error model, whether it's random errors or erasure errors or even adversarial errors. And moreover, it's robust to approximation, even if we were to recover psi approximately. With that in mind, the question we study in this work is, can we approach this quantum singleton bound for adversarial errors efficiently, using efficient codes? And our main theorem answers this in the positive, in that for every constant rate r and slack parameter epsilon, there's a family of codes which corrects from a fraction of errors approaching the quantum singleton bound up to some inverse exponential recovery error, which depends on the block length n, on alphabets of constant size, which just depends on the slack epsilon. And here by alphabet, I mean the local dimension or the small Hilbert spaces H. Great. So if you're a classical coding theorist in the crowd or tuning in, you may be asking whether approximation is actually necessary. And to explain this, we need two further ideas in coding theory. The first of which says that any error correcting code, whether classical or quantum, of certain distance d, it can't possibly exactly correct from more than d over 2 adversarial errors. And the intuition for why is that if you were to give to the decoder a point which lies exactly in between two code words, so at distance d over 2 from both, there's no possible way for the decoder to distinguish which was the true code word, I suppose. Thus, applying this logic to the quantum singleton bound, we conclude that no exact quantum error correcting code can correct for more than d over 2 or 1 minus r over 4 errors. Nevertheless, in a very surprising result, Propo, Gottesman, and Smith showed that if you were to allow just an inverse exponentially small error, you can correct up to a fraction of errors which approaches the no cloning bound, or 1/2. However, unfortunately, their construction had an asymptotically decaying rate and an exponentially large alphabet size. And it's these two goalposts that we're trying to bridge in this work. Now, for purposes of comparison, the classical singleton bound limits codes of rate R to decoding from at most 1 minus R errors. And again, this bound is quite robust. It works for random errors or for erasure errors, but there's no way to bridge this gap for adversarial errors. And this in particular is because we can't possibly decode from a fraction of adversarial errors of more than half the block length. The reason why is quite similar. If we were to take half of our code word and swap it with a valid half of some other code word, there's no way for the decoder to tell them apart. So in a sense, a result which bridges the adversarial error decoding radius and the singleton bound, which is the random error decoding radius, seems like a fundamentally quantum statement. Great. So while we can't decode uniquely up to this classical singleton bound, we can achieve a relaxed notion of decoding known as list decoding. So in a list decodable code, the goal isn't to just decode to the closest code word, but instead to output a list of code words which are near any given point. Now, to describe this using a diagram, suppose we have our code space in sigma to the n, where the blue dots represent code words. And let's say that the distance between any two of them is d. Given any point y in red, suppose we draw a ball of radius tau n around y. Then we say that the code is tau L list decodable if there's at most L such code words in any such ball. Now, there's a kind of nice interpretation to this statement when C is a linear code. So linear codes are specified by parity check matrices, H, and H is said to be tau L list decodable if there's at most L errors of bounded weight which agree with any given syndrome. So a syndrome here is just the product of the parity check matrix and the error. With that in mind, arguably the main technical contribution in our work is a definition and constructions of quantum error correcting codes which are list decodable. So to just set up some background, the family of CSS codes, or quantum error correcting codes known as CSS codes, are a certain quantum analog to linear codes, in the sense that they're specified by two parity check matrices, Hx and Hz, satisfying a certain commutation constraint. Now, what's quite nice about them is that we can treat their error model as in terms of a discrete set of errors, namely the Pauli errors. And these can kind of be understood as a combination of bit flip errors X and phase flip errors Z. With that in mind, the definition we introduce of a CSS code is that a CSS code is tau L list decodable if there's at most L distinct errors, say E1 through EL Pauli errors, of a certain weight tau n, at most tau n, which agree with any given syndrome S. Now here there's an important subtlety lying in the degeneracy of errors, which I'll refer you guys to the paper for. And I should say our definition refines a previous definition by Lung and Smith in 2008. To take a step back, in quantum error correction, we're dealing with quantum code states. So in principle, there's no real way for our decoder to output a list of quantum code states, because in a sense, that would imply cloning. However, what we can do is output a list of the classical description of errors. And to understand why this definition is useful, suppose we're given some code state psi, and we corrupt it with some error EI. Upon measuring the syndrome of this error, we can decode it to a list of candidates, E1 through EL. Naturally, we won't know which one of these candidates the error is, but we can cycle through them in the following sense. Suppose we attempt to decode by reversing or applying E1 as a correction. Then maybe we perform some post-processing, and subsequently we can try the next correction by reversing our correction E1, since these operations are all unitary matrices, and trying the next one by applying E2 dagger, and so on. And shortly I'll describe how this intuition is leveraged for decoding. Great. So the main theorem in our work, which allows us to construct these codes, is the following statement, which says that if we're given two parity check matrices, Hx and Hz, which are both tau L list decodable, then their CSS code is tau L squared list decodable. Applying this intuition to the capacity achieving list decodable codes by Gruas, Rami, and Rudra, known as folded Reed-Solomon codes, we're able to construct quantum list decodable codes, which are list decodable up to the quantum singleton bound, where the list sizes are just polynomial in the block length. Great. So the question you guys should be asking now is, how do we break ties in this list, trying to leverage list decoding for unique decoding? And for this purpose, we appeal to this intuition in a paper by Kramer et al. In Eurocrypt 2015, where the idea is to take our code state and we'll tag it with a certain quantum authentication scheme, and subsequently encode the result into the list decodable code. And here, the idea is that first, after tampering and decoding the list decodable code into a list of candidate errors, we can cycle through the list, and at each step, using the verification of the authentication scheme to check if the correction we applied was the true error. Now, as a technicality, what we actually use isn't an authentication scheme, but instead a pseudo-random family of stabilizer codes known as purity testing codes. But I'll say more about this shortly. Great. So to conclude our construction, note that authentication codes actually need a secret key. And in principle, the decoder doesn't have access to this secret key. So to be able to convey this information to the decoder, we leverage a technique known as code blocking, where in particular, we take our secret key K and we encode it into a classical, robust secret sharing scheme in purple. And then simultaneously group the robust secret sharing scheme with the quantum list decodable code, where at the end, each symbol of the resulting construction is going to have a quantum register and a much smaller classical register. And here, the intuition is that by hiding the secret key into the robust secret sharing scheme, we ensure that the list of errors that the adversary produces is independent from the key that we hid inside. Great. So the last thing to say is that, technically speaking, the folded Reed-Solomon codes that we leverage in our construction, they're actually not constants over constant size alphabets. So to achieve the advertised result, we actually need to decrease this alphabet size. And for this purpose, we appeal to a technique by Elon, Edmonds, and Luby in 1995, known as distance amplification and alphabet reduction, where here, the idea is to take our original code word, we concatenate it into some inner code, and then we permute the symbols around using an expander graph. And the intuition is that even if we were to tamper with a certain fraction of the symbols in the resulting code, after we invert the permutation, all these errors are kind of distributed, roughly balanced between the inner codes, such that on average, most of these codes are decodable. Most of these errors are decodable. And if we were to do this using a small random inner code over constant size alphabets and a good expander, we're able to decrease the resulting alphabet size to constant while preserving the decodability property. To make this work actually for list decodable codes, we need to leverage a notion of list recoverability, similar to Guruzwami and Rudra, which I won't really have time to get into. And finally, to the extent of our knowledge, this is the first application of AEL amplification to quantum error correction. And so along the way, we're able to apply this to the recent constructions of good LDPC codes to boost their rate distance trade-off up to the quantum singleton bound. Excellent. So to conclude with some words on subsequent and future work, in recent work at Eurocrypt this year, I worked on refining our list decoding to approximate quantum error correction reduction by leveraging a certain quantum analog to algebraic manipulation detection codes by Kramer et al., which are kind of lying at the intersection of coding theory and cryptography. And to take a broader perspective, this idea of breaking ties in the list, is closely related to notions of error detection and tamper detection. And on that note, I want to refer you guys to a very interesting recent line of work on tamper detection and non-malleability in the quantum setting. Finally, this development of quantum distance amplification, or quantum AEL, has found recent applications to local testability and local recoverability as well. As for future work, classical list decoding has found several connections and is quite deeply connected to notions of pseudo-randomness, like randomness extractors. And it would be very interesting to see whether quantum list decoding enjoys some of these connections as well. And finally, a personal favorite question is, how close to the quantum singleton bound can we actually get efficiently? So in our construction, we're able to approach the quantum singleton bound over adversarial errors up to an arbitrary constant, but where this constant appears as a trade-off to the alphabet size. And thank you very much.